It is a great pleasure to be selected by Royal Swedish Academy of Sciences to receive the Crafoord Prize, established through the generosity and far-sightedness of Mr. and Mrs. Crafoord. It is likewise a great privilege to give a talk on climate change, on the subject that I have enjoyed studying throughout my career. The atmospheric concentration of carbon dioxide has been increasing, as shown in these figures, and has increased over 30% since the pre-industrial era. Global mean surface temperature has already increased by 1 degree centigrade. It is projected to increase an additional 2 to 3 degrees centigrade by the end of this century. During last several decades, we have studied the mechanism of climate change using numerical model of climate that is based upon laws of physics. On this occasion, I would like to discuss the role of greenhouse gas in global warming. As shown in this figure, heat balance of our planet is maintained between incoming solar radiation, indicated by red arrows over there, and outgoing terrestrial long-wave radiation coming from Earth, as indicated by yellow arrows. And given the outgoing long-wave radiation observed from satellite go around and observe the long-wave radiation coming out from the atmosphere, one can compute planetary emission temperature from the Earth going outward using Stefan Boltzmann's law of black-body radiation. This is thermodynamical terminology, forget me that. And the temperature that's obtained is minus 18 degrees centigrade. That is much lower than the temperature of Earth's surface, which we enjoy, which is plus 15 degrees. The difference between these two is owing to greenhouse effect of the atmosphere. So that greenhouse gas usually considered to be air pollution and so forth. But it's turned out that greenhouse gas is indispensable for our life. Without greenhouse gas, we can't live on this planet, which would be minus 18 degrees centigrade. And existence of greenhouse gas is already established by the satellite observation of outgoing radiations. And the next figure I just created to indicate, this is what I just said here, as you can see, how the effect of the greenhouse gas, which is 33 degrees centigrade. The next figure is constructed in order to illustrate graphically the greenhouse effect of the atmosphere. The slanted line, oh, I should do this. This one. This shows the distribution of temperature in the troposphere, which increase almost linearly with respect to height. And the black dot, which is on, oh, I keep pushing the wrong button, in the middle of troposphere, located in the middle troposphere, indicates the effective emission center of outgoing terrestrial radiation. As pointed out already, its temperature is minus 18 degrees here, and it's colder than the surface temperature by as much as 30 degrees centigrade. This is a greenhouse effect of the atmosphere. Here, I would like to explain why the atmosphere has such a large greenhouse effect. The radiative transfer in the atmosphere obeys what we call Kirchhoff's law, which is the law of thermodynamics. Forgive me the little technical. The law requires that at each wavelength, absorptivity of a substance is equal to emissivity, which is defined as a ratio of actual emission to theoretical emission of black body. Because Earth's surface has emissivity that is close to 1, it emits upward flux of long-wave radiation almost as black body. Black body of 255 degree Kelvin. Sun emits almost black body radiation of 6,000 parts per million, just for your information. As this upward flux penetrates into the atmosphere from outside, penetrating the atmosphere, it is depleted due to the absorption by greenhouse gases in the atmosphere, but it is accreted, the emission from the atmosphere itself, according to Kirchhoff's law. Because temperature of the atmosphere as a whole is colder than temperature of Earth's surface, as you can see in this figure, it is expected that depletion of upward flux is larger than its accretion, reducing substantially upward flux of long-wave radiation emitted by the Earth's surface before it reaches the top of the atmosphere. Thus, atmosphere as a whole reduced by about 40% the upward flux of long-wave radiation emitted by the Earth's surface, helping to maintain warm and habitable planet at the Earth's surface, which we enjoy now. I think it's easiest way to explain this greenhouse effect just acts like a blanket for us, you know. And if you have more greenhouse effect, temperature is warmer. That may be the easiest way to explain greenhouse gases, global warming. But I would like to talk a little bit about the mechanism of global warming for the convenience of later explanation, which is main topics I'm going to get into. So try to explain why global warming occurs. Now, if the concentration of greenhouse, such as carbon dioxide, increases, the absorption of upward flux increases if the atmosphere gets more opaque before it reaches the top of the atmosphere. Thus, absorption of upward flux from the lower layer of atmosphere increase more than the absorption of upward flux from the upper layers. If you suppose you have an infrared eye and look down the atmosphere, and you can see lower part of the atmosphere is hard to see because atmosphere is opaque. You can see better upper part of the atmosphere. Suppose you make that atmosphere more opaque, make it much harder to see the lower layer of the atmosphere than the upper layer of the atmosphere. This means the more the opaque the atmosphere, higher the altitude of effective emission layer of the atmosphere. Can you understand that? Yeah. And so the more greenhouse gas you have in the atmosphere, effective center of emission layer go up. And so I just go to next one. Yeah. As indicated by the point A, allow go upward. Now, because temperature of troposphere decreases with increasing height, so that effective emission temperature go up higher, that means it's reduced outgoing radiation. The more opaque the atmosphere, higher is the effective center of emission, thereby reducing outgoing radiation from the top of the atmosphere. So in order to restore the heat balance of the atmosphere surface as a whole, you have to warm up the troposphere. You have to warm up the Earth's surface, thereby restoring balance. This is the mechanism of global warming. The change in the concentration of greenhouse gas, this is an important point which I have to use in my talk, is not only decrease the upward flux of long-wave radiation, but also it affects the more the downward flux that reach a ground surface, which has a profound effect in climate change at the Earth's surface. So I suppose suppose if the concentration of greenhouse gas increases in the atmosphere, the infrared opacity of atmosphere increases, as I noted already. Thus, the absorption of downward flux from the higher layer increase more than the flux from lower layer due to the difference in the thickness of underlying layer. Getting confusing? Sorry. Yeah. So that the more atmosphere, more opaque the atmosphere, lower is the emission of the downward flux. Emission of downward flux originates from point B. So you made the atmosphere more opaque. Effective emission center come down, thereby increasing downward flux of long-wave radiation, thereby making the temperature Earth's surface warmer than less opaque atmosphere. So I try to explain this, and I hope I didn't confuse you. And over sufficiently long period of time, Earth's surface sooner or later return to the atmosphere all the downward flux of long-wave radiation coming from above. So, and then with heat energy returned upward in the form of sensible and latent heat flux, dry and moist convection. They bring back into the atmosphere. So that is why temperature just doesn't include just the Earth's surface, but return into the troposphere, all the way to the atmosphere. So the more CO2 you have, the warmer the not only Earth's surface, but also entire troposphere warm up. So this is the actual mechanism of warming, of global warming. But the magnitude of warming is such that consistent with the change in upward flux, which I discussed earlier. Maybe I better switch over to. An important factor that affects the magnitude of global warming is the positive feedback effect that involves water vapor. As we know, water vapor is the most powerful greenhouse gas in the atmosphere. And it's absorbed and emit over much of the spectral range of terrestrial long-wave radiation, and is mainly responsible for the powerful greenhouse effect of the atmosphere. In contrast to long-lived greenhouse gas, such as carbon dioxide, with a residence time of a few hundred years, water vapor has a short residence time of a few weeks in the troposphere, where it is added through evaporation from the Earth's surface and is removed rapidly through precipitation. Thus, the absolute humidity of air is bounded by saturation, preventing relative humidity from exceeding 100%. As we know, saturation vapor pressure of air increases with increasing temperature, enhancing the moisture holding capacity of air. Thus, absolute humidity of air usually increases with increasing temperature, thereby increasing the greenhouse effect of the atmosphere. It magnifies the greenhouse effect of long-lived greenhouse gas, such as carbon dioxide. It doubles or triples, depending upon what effect you put in there. It was towards the end of the 19th century when Arrhenius, famous Swedish scientist, made the first attempt to estimate magnitude of climate change in response to the change in the concentration of greenhouse gas in the atmosphere. Using one-layer model of atmosphere combined with heat balance model of Earth's surface. He's the first person to use the climate model, in a sense. Yeah. He estimated the change in surface temperature in response to large change in the atmospheric concentration of greenhouse gases. I am impressed very much that he realized already the importance of the water vapor feedback at that time and incorporated it into his computations. His paper was published in 1898. This is several years before the publication of Planck's quantum theory of black-body radiation. It is remarkable that Arrhenius conducted these truly pioneering studies. It was in the mid-1960s when Mr. Weatherald and I made an attempt to tackle this problem using one-dimensional vertical column model of the atmosphere, in which heat balance of atmosphere is maintained through close interaction between radiative transfer and convective heat transfer in the atmosphere. Using the model, one-dimensional column model, we computed the vertical temperature profile of atmosphere in radiative convective equilibrium. computation was repeated for 3 different concentrations of carbon dioxide. First one is 150 parts per million, then the 600 parts per million. For your information, 300 parts per million was the concentration of carbon dioxide near the beginning of the 20th centuries. It is approaching now 400%, as you know. In this case, this blue line is 150 parts per million radiative equilibrium temperature. Black line is 300 parts per million. And red one is 600 parts per million. If you look at the lower half of the figures, which is the troposphere, you can see temperature increase every doubling from 150 to 300 to 600. Every doubling, it's increased about equal magnitude. It's increased by about 2.3 degrees for each doubling. This is substantially rather than 1.3 degree centigrade that I got in the absence of the water vapor feedback, which I explained to you earlier, indicating the magnitude of greenhouse, the water vapor feedback contribution. It was a big surprise for us at that time to find out that stratosphere is actually, what I'm doing here now. This one. Stratosphere is actually cooling when temperature go from 150 to 300, 300 to 600. And for the economy of time, I'm not explaining this mechanism, which is fun to explain because it's related to ozone and everything. But let me skip these things here. The next one, this one-dimensional model we did in 1960 was a first step towards developing three-dimensional structure of the climate model. And so let me explain one of the highlights of results obtained from climate models. This is, forgive me these terminologies, you just get a general impression of the model. I think you explained much better than I did so already. So, three-dimensional model, they consist of 3 components. One is the atmospheric general circulation model, which is indicated by green here. And then you have an ocean general circulation model, which is indicated by blue, and heat balance, water balance model of continental surface, which is indicated by brown box. And they are exchange heat, momentum, water vapor through the interface. Using this model, we simulated on the computer 3-dimensional structure of the coupled ocean atmosphere system. We then evaluated the response of model climate to gradual increasing atmospheric carbon dioxide. Although initial version of the model was constructed in the late 1960s in collaboration with Kirk Bryan, it took 2 more decades before the model climate was made realistic enough for a global warming experiment, which I'm going to describe here. Here, I would like to present the results from the experiment that we conducted in the late 1980s, about 30 years ago. In the experiment, the model was forced by gradually increasing atmospheric carbon dioxide at a constant compounded rate of 1% per year. This rate is roughly equivalent to the rate of increase in radiative forcing since the late 1980s, not including ozone change. The upper frame of this figure illustrates the distribution of predicted change in surface air temperature by the 70th year of the global warming experiment, when atmospheric concentration of carbon dioxide doubles, which actually happening toward the latter half of this century. So it may be compared with the bottom frame of figure, which illustrates geographical distribution of observed temperature during last several decades. When multi-decadal rate of global warming, last several decades, when that multiple decadal rate of global warming has been the most pronounced. In order to facilitate comparison between geographic pattern of predicted observed change that are different by a factor of 5, colors are chosen such that value at the color threshold in the upper frame of figure are 5 times as large as those in the lower frame of figures, highlighting the pattern of warming rather than its magnitude. And comparing a pattern of predicted change with that observed change, one notes that surface temperature increase almost everywhere, with land area warm faster than adjacent ocean area in both model and observation. As explained already, the downward flux of long-wave radiation increases as greenhouse gas increases, and that's why it's warm up everywhere. The very simple explanation. And thereby increasing surface temperature. As this figure indicates, the magnitude of warming is larger over continent than ocean. You can see, this place. See, this is North America here. This is Eurasia, and ocean is less. And another thing that happens is that temperature increase about 2 degrees, 3 degrees, 5 degrees. It's increase with increasing latitude. And this is due to the fact that snow cover retreat forward in high latitude, reflect the sunshine. And there are the other reasons, but let me skip that. And so that's what is happening here. Why it's what we call polar amplification of global warming. But what is so surprising about is that warming is very small. Look at here, 1 degree contours. Northern hemisphere, very large warming. Its contrast is huge. And 1 minute, that's maybe 3-4 minutes. Yeah. So, but then look at the observed, and this is 60 degrees south. Forward of 60 degrees, you don't have any data, no data over there. So it's not shown here, but already showing that there is practically no warming in southern hemisphere. Why this happens? And I'm not going into detail because already I have only 1 minute, but no warming in southern hemisphere. Actually, there's many reasons for this. But the reason what is happening in this model is actually in the circumpolar ocean in winter, sea ice formed. And when sea ice forms, then they brine rejection. They create a patch of dense cold water which sinks deeply. And then, so that warm anomalies sink very deeply in the ocean, thereby reducing the warming. Thermal inertia of ocean become very large because of large convection, deep convection. And so this is why the warming is in turn resulting in the corresponding increase. So warming is very small over there. Now, the global warming affect not only global mean rate of precipitation and evaporation, but also their geographical distributions of precipitation and evaporation. When temperature increases in the troposphere in response to the increase in the concentration of greenhouse gases, it is expected that horizontal okay, now they should go. Yeah, that's me. Global warming involves change in not only in temperature, but also in the rate of evaporation and that of precipitation. If the concentration of greenhouse gas, such as carbon dioxide, water vapor increase, then the downward flux of long-wave radiation increases, as I explained already, illustrate using this left-hand side of features. Thus, it is expected that rate of evaporation also going to increase because more energy available for evaporation. The global scale increase in the rate of evaporation, in turn, result in the corresponding increase in the rate of precipitation, thereby accelerating pace of hydrologic cycle, so that global warming accelerates the hydrologic cycle. Global warming also affects not only global mean rate of precipitation and evaporation, but also their geographical distributions. When temperature increases in the troposphere in response to the increase in the concentration of greenhouse gases, it is expected that the horizontal transport of water vapor by large-scale atmospheric circulation also increase in the troposphere, as the absolute humidity of air increase with increasing temperature. This is the main reason why the distribution of precipitation change differ from that of evaporation due to global warming, affecting substantially the distribution of water availability, such as the rate of river discharge and soil moisture at continental surface. As indicated in our numerical experiment, river discharge is going to increase in many water-rich regions of the world, increasing frequency of flood. On the other hand, soil moisture is going to decrease in many semi-arid regions of the world, increasing frequency of drought, as happening in the southern Europe, southern California, Australia, sub-Saharan region, Sahel, and grassland of Africa. The implied amplification of existing difference in water availability between water-rich and water-poor region could present very challenging issue for the mankind. Thank you. Sorry, time excess.
Questions? Yeah. Any questions to Professor Manabe after this very enlightening lecture about the complexities of global warming? I have a question. What do you think is the most complicating process during your experiments?
Actually, what I tried to do was there's many complicated processes in the atmosphere. The more you look at, the more complicated, just like human bodies.
Yes.
And I decided whenever I want to make some process complicated, then I said, is this additional complexity is warranted in light of my ignorance? So I made it as simple as possible. Because just like a fractal world, you look at another scale, it's almost as complicated as atmosphere itself.
Yes, yes. Yes, Dorte?
University of Copenhagen. I would like to ask, what do you answer? What do you answer when people in the US say, I don't believe in global warming? What do you tell them?
Yeah, I was asked that question yesterday, but one of the important things is the people just don't want to believe, what they don't want to believe. And also, they don't realize this is not just model result is telling something, but also this climate change is confirmed by a great deal of observation, not only ground observation, but also observation from satellite. They can monitor just about any important variable from above the sky. And so but the people who are skeptical about it is never actually look at these results themselves. And they believe what they want to believe.
Yes, I think that's very true. Birgitta, a short question.
Okay, I hope it's short, or you can give a short answer. I think you were into something very important in the end of your talk when you showed that it's not only a change in global average temperature that's important, and it's also other parameters, and also frequencies of extreme events. Is that something that you would like to comment on, extreme events? Extreme temperatures, extreme precipitation, droughts, and so on?
Yeah, these events, I think there is the thing, for example, as I pointed out, frequency of drought is increasing. So many key places, as you know by reading the newspapers and so forth. And I think what is important is one of the things is frequency of big flood occurs in Thailand, Pakistan, Bangladesh. And they really increase tremendously. And so I think we have to carefully monitor these things, look at the past record, and then look at very careful analysis of worldwide precipitation record and so forth, and keep monitoring into forward, so that keep confirming result of experiment by very careful analysis. And we have a big task at hand too, so that we can really trust these prediction is actually happening.
Thank you very much. Okay, I think we have to go on.